Okay, so at this point, we have covered how to find all the information given our equation here. And so now it's time for us to go ahead and try to do one of these problems in its entirety without any interruptions. So the first thing that we're going to do, again, just to kind of walk us through it, is that we need to factor the numerator and we need to factor the denominator. The way that we can use our calculator to do this is we're going to input them one at a time. We have 2x squared minus 4x minus 6 as our numerator. You will notice that all these numbers are in fact divisible by 2, so I'm going to factor out a 2 first. I'm going to graph it, and we will notice that there are two x-intercepts on here, located at -1 and +3. Those are the zeros for the numerator, -1 and +3. The linear factors that go with -1 is x plus 1. The linear factor to go with 3 is x minus 3. That takes care of the numerator for us. Now it's time to move on to the denominator. We have x squared plus x minus 20. Again, I will graph it. We have an x-intercept at -5 and at +4, so those are the zeros, -5 and +4. The coefficients here are 1, 1, and -20. The only number that all those are divisible by are 1, so that means I don't need to factor anything out. The linear factor to go with -5 is x plus 5. The linear factor to go with 4 is x minus 4. And now, both the numerator and denominator are factored. The degree of the numerator, once again, is we look for the highest exponent. The highest exponent on an x is 2. I'm going to go ahead and put a box around this term here. And I'm going to put a box around this term down here as well, because that is, again, our highest exponent. The exponent here is 2. That's our degree. The exponent down here is 2. That's the degree of the denominator. The leading coefficient is here inside the box. The coefficient of the top one, the numerator, is 2. The coefficient of the denominator is 1. And now we have all the information that we need to determine the rest of the information here. Removable discontinuities. Do we have any zeros that appear in both the numerator and denominator at the same time? Well, -1 and 3 in the top, -5 and 4 in the bottom, they don't share any numbers in common. So what this means is that there are no removable discontinuities. So we will write none. For vertical asymptotes, we are looking for the zeros that appear in only the denominator. We have -5 and +4. So therefore we have two vertical asymptotes here. X equals -5 and x equals +4. I'm going to go ahead and plot those on here. A vertical dashed line on -5 and a vertical dashed line on +4. The x-intercepts are the zeros that are only in the numerator, -1 and 3. So our x-intercepts are going to be -1, 0 and 3, 0. And I'm going to go ahead and plot those as well, -1, 0 and 3, 0. The y-intercept, let's go ahead and make sure we don't have any discontinuities on our y-axis. There are no asymptotes or holes on here, so we are going to have a y-intercept. To get the rest of this information, I'm going to go ahead and put this thing in y equals already. So, alpha y equals, to do the fraction, we got 2x squared minus 4x minus 6 divided by x squared plus x minus 20. Let's graph it to see more or less what it's going to look like. And you will see that it is a shape unlike any that we have seen before. But that won't be too big of a deal because we are just going to plot it. Now, we do have a y-intercept right here, so let's go to the table to find out exactly where it is. The x-coordinate is always 0. And the y-coordinate shows up here on the table, 3/10. I'm going to go ahead and put that on here as well. For the horizontal asymptote, we need to look at the degrees. Once again, the degree of the numerator is 2, the degree of the denominator is 2. The degrees are equal to each other. According to our notes here, which we are going to look at right now, since the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote is located at y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. So the leading coefficient of the numerator is 2. Leading coefficient of the denominator is 1. 2 over 1 is just 2. So here on the line, I'll create a horizontal dashed line at 2. At this point, we are ready to now graph it, but in order to do that, we should fill out the table. We want to make sure to include all this stuff, and sometimes we can't get a good even scale. I want to graph stuff on this side, I want to graph stuff in here, and I want to graph stuff on this side, and it's a pretty big span for the number of cells that we actually have in our table. So I'm going to go ahead and get just a little bit chaotic with this. I'm going to start off with this -5 and put it right here on the second cell. So that way I can write the words undefined. Also, I want to include all three of these intercepts in the part that's in between, and plus maybe one more point so we can see what happens over here. So I'm going to put my other asymptote over here, which is at 4. It is also undefined. And let's see here. We have an x-intercept at 3, 0. We have a y-intercept at 0, 3/10. We have another x-intercept here at -1, 0. And it looks like I ran out of room for this other point. It's all right. I can plot that later on. Now, for a point over here on the left side, let's go and find out what our calculator says at -5. Sorry, not -5. Let's do -6. That gives me a 9. So I'm going to go ahead and plot that. -6 gives me 9. Let's see here. Just to plot a couple of other points, like let's try -3. We have -12 over 7. Let's do a quick trick. I don't know what this is in decimal form, but if I go to y equals, and I say this function, to make it into decimals, I'm going to do alpha trace to do y1, then do math 2. y1 is now going to be in decimal form. So I have my fractions written here, but now I have the decimal version written right there as well. I said we do -3, and it's -1.714. So -1.714 is kind of close to 2, about right there. And then we can get a very nice looking graph for this. We wanted to check out the -4 as well, -5.25. That way we could try to get as much accuracy as possible. And here on the right side of our asymptote, let's go ahead and look for number 5. 5 gives me 12 over 5, which is 2.4. 2.4. But you'll notice that it does actually go below the asymptote here. I've told you before that it may cross over. And then it starts going down even more. And it keeps on going down, but then you notice that it bounces back up. So literally what happens on this side is that it may cross over our horizontal asymptote, but it does come back. And gets closer to it as we reach infinity. Over here on the left side, just to copy what we have, again, it starts making its way to the left right there. And of course, we can always plot more points for as much accuracy as possible. And for the middle part, it arches off over here. And then it stays more or less straight here and then suddenly dips down real fast. The domain is a simpler one to get between domain and range. It's all real numbers, but it does not include the zeros from the denominator. X is not equal to -5, and x is not equal to 4. The range is a little bit tricky because of the fact that, first of all, we cannot disinclude 2 because our graph clearly does cross over that asymptote. So really the only part that's not included in our range is the little gap from here and here. Really the only way that we can figure this out is to find out how high this middle lump goes and how low this one goes. That is something that we will save for another time. So this is how we tackle down one of these problems. Now this is a case in which we have no holes, but we do have vertical asymptotes, a couple of them, and the other situations that we have to deal with. So this is one of the many shapes of the graph that we can actually get from rationals.